Thank you very much. And first of all, I have to extend my thanks for inviting me to this occasion. And it already has improved the paper I'm going to present today, because due to this discussion we had and some of the talks by Francesco, and I was looking up some references and found that in the article I put on archive, I have overlooked stuff. Articles by Konstantin Bagrashin and Andrea Possedicano, and also the PhD thesis by Stefan Schmitz, who contributed something to this. So I updated the archive version already, so you can see today the latest version. Unless I find something more, the update's gonna come. Anyway, so what I'm gonna talk about is laminated metamaterials, and I just put the number here. And what I'm not going to talk about is what a metamaterial is physically, because I'm not a physicist. So there's many people saying a metamaterial is, and since I'm not going to talk about, I will just leave it at that. What I'm going to consider here is a divergence form problem of this type with U in H10 omega bounded domain in RD, and A is going to be a function, a very particular function, but for the time being I would just say it's a scalar, and it attains values in R. So usually you would assume something like the real part of A is strictly positive. This is not what I'm going to do here. I particularly ask for A taking real values. And one of the maybe easiest examples you can think of is take omega to be a rectangle and half this rectangle and put a 1 in the left half and the -1 in the right half. And if you then look at this partial differential equation, you're going to run in troubles, because this is not, looking this as a partial differential equation in L2, say, so f is in L2 of omega, then this is not going to be solvable. So in particular, the 0 there is a point of essential spectrum due to the symmetry of the domain, and the 1 and -1 respecting the symmetry, so that you have the eigenvalue 0 of infinite multiplicity. So this is complicated, and this has been found by Jussi and Dirichlet, since I'm a homogenization guy, 1 and -1 is a bit too boring for me. So I was trying to understand this problem in a more complicated setting, when I not only have 1 and -1, but 1 -1, 1 -1, and even more so. So basically, what I'm trying to address is, what is the limit of having infinitely many layers there, jumping from 1 to -1? And since the original problem is ill-posed, I mean, the problem with, say, n layers is still ill-posed, obviously. So the question remains, what is the limit then? So I'm desperately trying to understand this. And what I'm going to convince you about is two things in my talk. First one, that the limit is highly irregular already in one dimension. So not talking about a rectangle, but a line. And then I'm going to tell you why this is irregular, and I'm going to measure this irregularity also. And the measurement of this irregularity is by introducing a certain spectrum of the operator. And you could say, well, there is a spectrum already. This is a divergence-form problem in L2, so let's consider this. But this is not the precise one I'm going to talk about. What I'm going to talk about is the inner spectrum of A, and I'm introducing this right now. So take a step back and try to understand a divergence-form problem in this form. With F in H minus 1. And then A is an arbitrary bounded linear operator in L2. And if you want to solve this, you might be tempted to apply the Lax-Milgram theorem, but you cannot because it's not strictly positive. So you try to understand what this equation that is written up here actually means. And if you ask for U to be in H10, then no matter what happens, grad U is going to be in the range of the gradient. Okay. So if Yoda, similar to Olaf's talk this morning, is the embedding from the range of the gradient into L2, then you can just project onto the range of the gradient and nothing happens. But then A is an operator from L2 to L2, so you need to compensate for that. So you write a Yoda again, which again doesn't do anything. This is just a projection on the range of the gradients. But then the divergence is the adjoint of the gradient. So the kernel of the divergence is perpendicular to the range of the gradient. So if I put in Yoda star here, still nothing changes, because 1 minus Yoda star precisely projects onto the kernel of the divergence. And now I look at this and I use I gather this guy, this one, and this one. And then I see Yoda star gradient is now a mapping from H10 to the range of the gradients. And since omega is bounded and I apply Dirichlet boundary conditions, the range of the gradient is a closed subspace of L2. So this guy is 1-to-1 and onto. So it's isomorphism. Similarly, this guy is too, because this Yoda factors out the kernel, and this divergence thing is also an isomorphism. So you get that this operator is invertible from H-1 to H, from H10 to H-1, if and only if this guy is. And this I write down, so this is a star. Invertible as operator from H10 to H-1, if and only if 0 is in the resolvent set of Yoda star A Yoda. Okay, and okay, so I have an operator that is invertible from H10 to H-1, and this is an operator that maps range of the gradient to the range of the gradient. And I have a perfect equivalence of this invertibility of the one with the other. So I'm just saying that I'm defining the inner spectrum with respect to the range of the gradient of A to be those lambda in C such that A minus lambda is not a bounded linear operator, the inverse of this. It's not a bounded linear operator from the gradients into the gradients. And I call this the inner spectrum of A. And this is going to be the measure I will use to show that the this flipping limit here is highly irregular. And to understand this, I'm going to restrict the next couple of minutes to the possibly easiest case of sign changing coefficients in this business, namely to the one-dimensional case. Because in that case, you can actually compute stuff. So now 1D. So let's do this explicitly. So in 1D, G0 of omega, this is the range of the gradient. So omega is a interval, 0, 1, say. So this is the range of this partial derivative applied to the things with boundary conditions. And as I said, this is the orthogonal complement of the kernel of the divergence, which in this case is the derivative without boundary condition. So the kernel of the derivative without boundary condition is 1, the constant function. So this is just your orthogonal complement of 1. And with this, you can actually, using m of a or m of beta to denote the integral from 0 to 1 for any integral function beta, you can actually compute what the inverse of Yoda star A Yoda is in this particular case for A being a function. So let A be an L infinity of 0, 1. And this is, I found this in Stefan Schmidt's PhD thesis. And this Yoda star A Yoda inverse applied to psi, which is now perpendicular to 1, is given by A inverse psi minus A inverse over M of A inverse times M of A inverse psi. So a perfectly explicit formula. And you can see that this works out so that it maps functions that are perpendicular to 1 to functions that are perpendicular to 1, because if you integrate this from 0 to 1, so apply M of A inverse, then you see that this cancels and this is just the same. So you get 1, and you get 0. So, and this is nice. And with this, you can then obviously compute the inner spectrum in this particular case. I'm going to use a particular case now, namely that A looks as follows. On the interval, it's alpha 0, alpha 1, it's piecewise constant up until alpha r, with all those alphas being real numbers. And then the inner spectrum in this one-dimensional case of A consists of all those numbers, alpha 0, alpha r, okay? Which makes sense because if you subtract alpha r here or some alpha j, you cannot invert this. But you also see that you kind of need this mean to exist. So what you also will have is those lambda in C such that alpha minus a minus lambda inverse is not in infinity. Sorry. The mean is 0. Sorry. So that, because if that was 0, then you cannot define this inverse here. Okay, and you can actually do the math, and that is equivalent. Okay. So in this easy case, all is fine. But what about the higher dimensional case now? No. I just want to quickly comment on up until when I have 12, right? So which is 10 minutes from now. Okay. So if A is now periodic, changing these things periodically, so I extend this left to right on the whole of R periodically, then I can consider AN dot, which will boost all those oscillations that are initially given on the whole of R to the interval. So it's going to oscillate faster and faster and faster. So this picture is going to be the above picture. In the 1D version is going to be the thing. And then what happens is that A inverse dot converges to the integral mean of A inverse in the L infinity weak star topology. Standard result. And this leads to that the divergence-form problem which I'm going to write a bit over-sophisticatedly like this. This guy, if everything is nice, say A is positive, converges to minus diff 1 over integral A inverse grad U equals F. So with this convergence arrow, I mean that UN is converging weakly in H10 and that the solution satisfies this equation. So you see, you run into a problem when the integral mean of A is 0, which is precisely the case if it oscillates from -1 to 1. And one can then cook up a definition of homogenization, which I'm not going to present you, but I'm just saying you that it makes sense to consider this guy. And if A inverse was, so if the integral mean of A inverse is 0, then this 1 over A inverse is the inverse relation of the 0 relation. So this guy is then if this has a relation. So what is the spectrum of this? Spectrum is I add lambda times identity. I need to invert it and look whether I get a bounded linear operator. But whichever lambda I add, I will always get the 0 operator after inverting. So the spectrum, the inner spectrum of this guy is empty. I call this infinity. And in higher dimensions, something similar happens. In higher dimensions, considering everything that I just did, and you have the oscillatory behavior from -1 to 1, you need to work a little that you can cook up a notion of homogenization that makes sense here. But then, due to the presence of other dimensions, the spectrum is not going to be empty, but the whole of C. So you have a similar behavior for the limit. However, this relation is not going to have a full range. So this is one of the strange features that you get from, so my C's, this is complex numbers. So you get from empty to the complex numbers, whole of complex numbers, by just changing the dimension. And then you would say, okay, if this is all, then fine. But actually, it turns out that this homogenization process is very subtle in higher dimensions, and it depends on whether the integral mean of your function you're considering is 0 or not. So this is happening if the integral mean of the inverse was 0. If the integral mean of A was 0 and the integral mean of A inverse wasn't 0 in higher dimensions, then this spectrum is going to be countable with accumulation points at 0 and at infinity. And if you wanted to write the equation that ends up from this part to this part, if you wanted to write down this equation, this is going to be a 4th order differential equation, which is completely unexpected, at least to me. When I found it, I was like, what is happening here? And the case, if both of these guys are non-zero, is fine again. Then it basically happens the same thing that happens if your oscillations would be all just strictly positive. And with that, I'm going to close. Thank you very much.